All right, so starting from here, we're going to try and take the ideas that we've talked about, a transformation from the UV plane into the XY plane, and use these concepts to develop a means of evaluating double integrals with a change of coordinates like this. So the idea is that we would normally be starting with a function of x and y, and we want to integrate that function over some region in the xy plane. The perspective we're going to take for the justification of a change of variables is that this region here may be kind of complicated or difficult to integrate in rectangular coordinates. It's not the only reason why you may do a change of variables, but it's the easiest one to justify what we're about to do. An example could be if this was a circular region, or like an annulus or something like that. We know that those types of regions are much better described using polar coordinates. So sticking with rectangular in those cases is not the best route. The UV plane over here is going to be the new variables that we introduce, and if we choose these carefully, the corresponding region in the UV plane is going to be a rectangle where the sides of that rectangle are parallel to the u and v axes. We know that rectangles like this one are the easiest things to integrate using double integrals. So that's our perspective. We want to perform a change of variables that takes a region that's potentially difficult to integrate in rectangular coordinates, and then that change of variables converts this into a rectangle with sides parallel to our axes. So let's assume that the region that we're being asked to integrate over is R, and then let's suppose that we can find a transformation from the UV plane into the XY plane such that the UV plane contains this region S, which is the kind of rectangle we just described, whose image is R, okay? And t is going to be defined by these two functions here. X is going to be g of uv, y is going to be h of uv. These are the functions that carry points in the uv plane into points in the xy plane. Okay? And then what I'd like to do is define a couple of objects of interest here. So first of all, the position vector of the image of uv. So if uv is any point here, in particular a point in S, it's going to map to a point in R, and I want the position vector of that point to be R of UV. Now I know that the position vector of any point in the XY plane will have components that look like the coordinates of that point. And the coordinates of the point, xy, are given in terms of guv and huv. So that's why the position vector looks the way that it does here. Next thing I want to do, this is the position vector for a single point, but can we come up with a vector function to describe the images of curves? In particular, the lines that make up the edges of this rectangle. So I'm going to start by focusing on this bottom edge of this rectangle right here. You notice the point of this rectangle that's closest to the origin, I'm just calling it u0, v0, so I can reference those coordinates. If v0 is the v coordinate of this point, then this line right here is part, or this edge of the rectangle is part of the line v equals v0. All of the v coordinates of all the points on this line are v0. That means as points, as I choose different points along this bottom edge of this rectangle, the v coordinate of those points is a constant, and it's only the u coordinate that's varying. So we can represent that this way. The position vector of the entire line v equals v0 would look like this. R of u, I'm just basically plugging a v0 into this up here, giving me this vector function. Now, an important thing to point out about this vector function, like I just said, v0 is a constant, and vector functions we usually think of their input as being a parameter, a single parameter. So in a sense, they're single variable functions with vectors as outputs. The variable in this case would be u, since v0 is being held constant. So that means if I wanted to find a tangent vector to the image of this line. And just to be careful about what we, paying attention to which region we're talking about. This is the image of the line v equals v naught. So if this is v equals v naught, its image is one of the edges in this region R. We mentioned in a previous video that the boundary of this region will map to the boundary of this region. So I'm going to assume that this edge down here is the image of this edge right here. And so when I talk about the image of the line v equals v naught, this is describing this edge, or this boundary curve, I guess I can call it. Now, it is a curve, and the image of the point u naught v naught, I'm calling that x naught y naught. I can find tangent vectors at this point to either of the two curves that contain that point, and also make up the boundary of R. So either this curve or this curve. If I were to find the tangent vector of this curve right here, the image of the line v equals v naught, it would point, roughly this direction. But we know that in order to find a tangent vector, we can take the derivative of our vector function that defines this curve and plug in the point that we want to take that tangent vector at. Well, in our case, if I have this vector function describing the image of v equals v naught, so this curve right here, and u is the variable, then I'd be differentiating this with respect to u. But I could alternatively think of that as a partial derivative with respect to u, since that's what a partial derivative is. You hold one of your variables constant, differentiate with respect to the other variable. So the tangent vector at the point x naught y naught to this part of R, this curve on the boundary of R, is the partial derivative of this function with respect to u, which is why we see R sub u here, with the point at the point x naught y naught, which again comes from plugging in u naught v naught. So we would plug in u naught v naught into this. V naught is already there because that's the constant, so it's really just u naught that's being plugged in here. I could alternatively represent that in this notation as well, which will become more useful for when we get to the Jacobian. Not alternatively, but similarly, if I wanted to find the tangent vector at this point to this curve on the boundary of R instead of this curve, I've just come up with an expression for this tangent vector, but now I want one for this tangent vector. I could follow similar steps, and the only real difference would be that I'm taking the partial with respect to v with each of these functions here instead of with respect to u. So these represent the two tangent vectors at this point, one along that curve, one along this curve. Okay. Now, if you go back to Calculus 1, when you first introduce the concept of tangent lines, you start with what's called a secant line as an approximation to a tangent line. So a secant line would be like if I took, let's go back up to this picture up here, if I took this point right here and joined those 2 points with a line as an approximation to the tangent line at this point. Replace the word line with vector. I could talk about a secant vector. We have an expression for the tangent vector here, but if I were to use this as an initial point and this as a terminal point, then the vector joining those 2 points serves as an approximation to the tangent vector. An image on the next page of these notes will show you what that looks like more clearly. If I wanted to find the secant vector for either this vector here or this vector here, notice that this point should be the image of this point right here. And this point, if I look at its coordinates, remember u is what's changing on this line. V naught is going to be the coordinate of my, or my v coordinate for this point. So we have u naught here. We're changing by delta u. That means that the u coordinate there would be u naught plus delta u, and this would be v naught here. Okay, so this point here should be the image of this point here, which means this point is plugged into R. So if I wanted to find the tangent vector or the secant vector joining these 2 points, then what I want to find is the difference between the images of these 2 points. That's what you're seeing right here. This vector A is you can see the 2 points that I indicated here and here are being plugged into R, and we take their difference. That would give us the secant vector joining these 2 points here. So A is the secant vector in R joining these 2 points, whereas B, which I'll go back down to, is the secant vector joining these 2 points. Okay. Now, returning to the tangent vectors one more time, we've done 2 different things here. We have tangent vectors and we have secant vectors, and what I want to do is connect those 2 somehow. So again, by definition, this is how we find the partial derivative, or the derivative of R with respect to u. This is just from the definition of the derivative. This is the limit as delta u goes to 0 of this expression. Notice the numerator of this thing looks a lot like, well, exactly like our vector A. So the way I think of this is if delta u is very, very small, meaning very, very close to 0, then R sub u is approximately equal to this quotient right here. So if I assume that delta u is small, I can treat this almost like it was equal, multiply both sides by delta u, and I get this approximation. So this is our vector A that we defined up here. Similarly, if I go through a similar argument, our vector B is approximately equal to delta v RV. Okay, so let me go to the next page because it's going to become more clear once we see what we're talking about in a kind of a graphic. So if you're looking at this part, these are the secant vectors for R that I was describing. And this vector would be R of u naught v naught plus delta v minus R of u naught v naught, and similar for A here. But those secant vectors can be approximated by these tangent vectors. Notice it's the tangent vectors that we talked about, but multiplied by a scalar, justified in that previous step on the last page. So delta A, because we know that we're trying to come up with a Riemann sum eventually with all of this, and delta A, which is the area of one of those little pieces that we divide a region up into, that's going to become something that we need in that Riemann sum. Delta A, which is going to represent the area of R. Notice that R has an unusual shape, so I don't have a method to compute its area directly that I know of, but I can approximate its area by the area of this parallelogram determined by these 2 tangent vectors. That's what is leading us to this next step. Delta A is approximately the area of this parallelogram, but from chapter 12, we know that if you have a parallelogram determined by 2 vectors, the area of that parallelogram is the magnitude of the cross product of those 2 vectors. Now those 2 vectors both had a scalar that was being multiplied to them, and using properties of cross products and magnitudes of vectors, we know that those 2 scalars can be pulled out of that magnitude, and we're left with the cross product of RU with RV in this magnitude right here. So the next thing we want to do is evaluate this cross product. Remember, RU, coming back over here, RU can be written in this form. Okay, partial of x with respect to u, I, plus partial of y with respect to u, j. So if I wanted to find a cross product for those 2 things, it would look like this determinant. You can work out the steps of evaluating this determinant. What they're doing is expanding along this column right here. But remember, you get the same thing no matter what row or column you choose to expand a determinant along. And what we end up with is this as our cofactor expansion for that determinant. So the cross product is going to point in the direction of k. And the k component is going to be this determinant right here. This determinant is what we call the Jacobian, and we have a definition for it down here. So the Jacobian of a transformation t given by x equals g of uv and y equals h of uv is given this notation. So you see this kind of, it looks like a partial derivative, but with x, y, and uv here. And it represents the 2 by 2 determinant with these partial derivatives of our function. Okay, so based on our previous discussion, that Jacobian would actually be the magnitude of this vector right here. So I can replace this magnitude of RU cross RV with that Jacobian, and this is where I get the approximation for the area of that region R. Okay, this is a very long derivation. We still haven't gotten to the part where we start talking about an integral or a double integral, and we'll get to that part in the next video.